This video contains the solutions to the planes and surfaces practice problems. For this first question, we're given a point and a normal vector and asked for an equation for the plane that passes through that point with that normal vector. And this is really the perfect amount of information that we want. This is exactly what we want to use our formula for the equation of a plane. That equation looks like this: a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Where x0, y0, and z0 are the point, so in this case that's x minus 0, y minus negative 2, and z minus 2. And then the a and b and c are the normal vector. So that's 1, negative 1, and 3. Now we should simplify this at least a little bit, where we should write this as 1 times x plus negative 1 times y plus 2, and then plus 3 times z minus 2. Just so that we can still read off easily the normal vector and the point, but you might see this simplified even further, where we'd actually multiply this out and collect like terms. So we get x minus y minus 2 plus 3z minus 6 equals 0, and then we get x minus y plus 3z minus 8 equals 0, or even x minus y plus 3z equals 8. So any of these are valid answers that you will see. It just really depends on how much do we want to simplify. All right, in this one, again, we're looking for the equation for a plane, but we're not quite given the information that we would like. We're given that we want our plane to be parallel to this plane, negative x plus 5z equals 9. But if we think of this as minus 1x plus 0y plus 5z equals 9, then we can see that the normal vector for this plane is the vector negative 1, 0, 5. And that, together with the point that we were given, gives us the information that we want. So again, our formula for the equation of a plane is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Our a is a normal vector, so that's negative 1, 0, 5. Our point is 0, 2, and 1. And so that is our equation. And this time I'll leave it like that, but again, we could multiply it out and simplify it if we wanted to. For this one, we're given 3 points, and we're asked why can't we figure out the equation of that plane? Well, let's go through the process of what we would do if we did want to figure out the equation of that plane, and then see what goes wrong. So the idea is that if we have a plane, and we have 3 points on that plane, we can use those 3 points to figure out a normal vector by constructing 2 of the vectors between those points. So maybe I'll call this vector u, and I'll call this vector v, and then we can figure out the cross product of those 2 vectors, which in this case, if I do u cross v, would point downward like that. And then that would be the n that I would use as the normal vector to that plane. So let's do that here. So let's call these points p, q, and r, and I'm going to construct the vectors pq and pr. And those will be the 2 vectors that I'll take the cross product of. So pq I get by subtracting the coordinates of q minus the coordinates of p. That gives me negative 1. 1 minus minus 1 is 2, and 0 minus 4 is negative 4. And then for pr, again I do the same thing, but the coordinates of r minus the coordinates of p. So 0 minus 3 is minus 3, 5 minus minus 1 is 6, and negative 8 minus 4 is negative 12. Now, if you're really got a sharp eye for this sort of thing, you might already notice that something weird is going on, because you might notice that PR is actually 3 times PQ. And that means that these 2 vectors are parallel. And so we should already be able to predict what's going to happen when we try to take the cross product. But just in case we weren't that observant, let's just blindly go forward and figure out what the cross product is. So we get ijk, negative 1, 2, negative 4, negative 3, 6, negative 12. We take our 2 by 2 determinants. They're going to be 2, negative 4, 6, negative 12 times I, minus negative 1, negative 4, negative 3, negative 12, j, and then finally negative 1, 2, negative 3, 6, k. When we do our calculations, we get 2 times negative 12 minus negative 4 times 6 times I, minus negative 1 times negative 12 minus negative 4 times negative 3 times j, and then finally plus negative 1 times 6 minus 2 times negative 3 times k. And those all work out to be 0. So that gives us the 0 vector. So at this point, we're kind of stuck, but what we should realize is that what really happened, the picture that I drew there is not a very accurate picture, because in this case, what happened was the 3 points that I had, because the vectors PQ and PR were parallel, it turns out actually that those 3 points all lie on a single line. And 3 linear points do not determine a plane. There are lots of planes that go through those 3 points. And that's why we can't find the equation of the plane that goes through those 3 points, because in fact, there's lots of planes that would do it. So if you're trying to figure out a normal vector to a plane using a cross product, if you get the 0 vector, first check and make sure that you didn't make an arithmetic mistake. But once you're sure that you did it correctly, then what that's telling you is that the 3 points that you had were collinear. So here we have 2 planes, and we're asked to figure out whether the planes are parallel or intersecting, and if the planes are intersecting, to find an equation for their line of intersection. So for this, we're going to be looking at the normal vectors. So n1 here is the vector 2, 2, negative 3. Again, we're just looking at the coefficients of x, y, and z. And then n2 here is the vector negative 10, 15. And again, we'd like to try to be observant and notice whether or not these 2 vectors are parallel. We can always compute the cross product between 2 vectors. And if we get 0 when we compute the cross product, that tells us that the vectors are parallel. But if we can find that one vector is a constant multiple, a scalar multiple of the other vector, then that's a much quicker and shorter way to figure out that the vectors are parallel. And in this case, we can do that because if we look at 2 and negative 10, well, 2 times negative 5 gives me negative 10. And this 2 times negative 5 also gives me negative 10. And negative 3 times negative 5 also gives me positive 15. So that's telling me that n2 is actually negative 5 times n1. So since these 2 planes have parallel normal vectors, they're parallel planes. So the planes are parallel. Same type of problem here. So again, we'll figure out the 2 normal vectors. n1 is the vector 1, 2, negative 1, and n2 is the vector 1, 1, 1. And we can immediately see that this vector n2 is not a scalar multiple of n1, because if it were, the scalar multiple would have to be 1. But if I multiply by 2, it doesn't work. I don't get 2 times 1 equaling 1. So n2 and n1 are not parallel. And so these planes are not parallel. So if we want to find the line of intersection of 2 planes, it helps to find a vector that points in the direction of that line. Now that's a vector that would lie in both planes. And so how do we use our normal vectors to figure that out? Well, we can take the cross product of those 2 vectors. As we explained in class, the cross product of those 2 vectors is a vector that's perpendicular to n1 and also perpendicular to n2. That means it's in both of the planes. So we'll take n1 cross n2, and this is the direction vector that we'll use for the line that we're trying to construct. I, j, k, 1, 2, negative 1, 1, 1, 1. When we work out that cross product, we end up with the vector 3, negative 2, negative 1. Now we have a vector, but to find the equation of a line, we also need a point. So we need any point that just happens to lie in both of these planes. And so what we can do to make our lives a little bit easier is we can pick one of the variables and set that variable equal to 0. Because y is the only variable here that has a coefficient that's not equal to 1, probably the most simplifying thing that we could do is to set y equal to 0. So again, this is just to find one of the many, many points that lies in both of the planes. In fact, we're specifically looking for the point that lies in both of these planes and the yz plane. Sorry, the xz plane. So we're going to set y equal to 0. That's going to give us the equations x minus z equals 1 and x plus z equals 1. So if we add those 2 equations together, we get 2x equals 2, so x equals 1. Plugging back in to solve, we get z equals 0, and we already knew that y equals 0, so we can use the point 1, comma 0, comma 0. And again, if we look back at our 2 equations, plug in 1 for x, 0 for y, 0 for z, you'll see that it makes both plane equations true, so this point really does lie on both planes. So we've got a vector, we've got a point, now we just have to remember how to construct a line from those pieces of information. And what we have to remember is that r of t is equal to r0 plus t times the vector v. In this case, my r0 is the vector 1, 0, 0. And my vector v, my direction vector for my line, is 3, negative 2, negative 1. And so that's going to give me the line 1 plus 3t, negative 2t, and negative t. And that's the equation of the line that I'm looking for.